I'm going to talk about the self-charging devices, energy devices, and I am currently an associate professor of nanoscience, optics, as well as material science in University of Central Florida. So, it's a privilege to present my research work to my home institution. That's a really great privilege. And I would like to dedicate this presentation to all my professors in SB College, and from 1983 to 90. So also, I would like to thank a few people, especially Dr. E.J. Matthew. He was I think he was a lecturer at that time when I was studying my BSc and MSc classes there. So he introduced me to the research, and I really acknowledge that effort at this point. He introduced me to the research. He introduced me to my PhD supervisor and helped me a lot in that sense. And another person I would really like to mention is Dr. Philip Casey. Though he didn't teach me at SB College, he joined SB College after I left, I think long after I left. But he helped me a lot in Cochin University of Science and Technology while I was doing my PhD. He was senior to me. And I would like to mention at least these two names, but all my other professors, so many names, George Sir, so many Tankacha Sir, and all those professors. I really dedicate this presentation to you all. So here you can see a picture of our BSc, Bachelor of Science class back in 85, 88. And I don't know whether you can see me here. I was sitting here, somewhere here. So that was the BSc class. And then this was the 88 and the MSc class. So we had both analytical chemistry and pure chemistry in SB College at that time. I was sitting somewhere here. Here you can see me. So that was my BSc and MSc classes in SB College, and SB College actually molded me to whoever I am right now. So I am very much thankful to SB College, and I acknowledge these things before I begin my talk. So as you already heard, I am from University of Central Florida. So University of Central Florida is a big university with about 73,000 students in the main campus. We don't have any affiliated colleges like you have there. It's the main campus. We have about 70,000 students or so, and all the faculty and non-teaching staff and all the other faculty, all the other staff. It makes up to about 80,000 or 85,000 people in the campus. So I have appointments with the Nanoscience and Technology Center, as well as College of Optics and the College of Engineering. And the College of Creole, the College of Optics and Photonics, is one of the top institutes for optics and photonics in the world. So we Creole offers a number of courses, facilities, and all those things. If you are interested in optics, you can apply in Creole. And also the material science, where I teach both in Creole as well as in material science, and also in Nanoscience Technology Center. This is the College of Engineering, one of the main buildings there. And we have right now, I think, more than 23 faculty there and a lot of facilities. For those who are interested, you can definitely apply. There are so many opportunities there. For example, you have a lot of career opportunities like high-tech industries, Lockheed Martin, Siemens, Mitsubishi, and NASA. NASA is our, Kennedy Space Center is our next door neighbor. So much good things, so many industries are there, and that is really good. So there are so many career opportunities. You have opportunity in University of Central Florida. If you are interested, you can go to the website ucf.edu, www.ucf.edu. So I would acknowledge my group. These are not the present group. There are previous and current students here, and these are some of the previous students who contributed to this work, and some of the current students. We have Kaushik, Sampath, Deepak Pandey, and Jingshin Lee, and a few other graduate students are going to join in fall of this year. And some of these postdocs, they already left. Dr. Srikanth Verma, he was a visiting scientist. Reggie Philip and Basdev Pradhan, he left, I think, towards the end of last year. So again, for professors or assistant professors and lecturers, there are so many opportunities, and even the government of India provides a number of fellowships which you can apply for. Typically, I give support letter to whoever asks me for such fellowships and such things. So if you are willing, you can contact me. And also, you need to remember there are a number of criteria. Government of India looks at that one, whether your publications and all those things. And if you have a really cool idea, you can contact me or any other process. It's not me. Anyone you are interested in, you can contact them and get an opportunity to work here. And these are some of the present students in my group. Actually, Priyanka left, I think, a few months ago to India. And these are some of the undergraduate students, and these are some of the current and past undergraduate students. And of course, the money, we need to bring money from the external agencies. The university doesn't support any of the research. So the NASA supported a part of my research. Florida High Tech, they supported me, as well as the NSF Career Grant, which is a very prestigious grant, and NSF Eager, and a few other grants from National Science Foundation, as well as Air Force Research Lab funding and Department of Navy funding. So this is the group. My group, at least maybe 8 to 10 months ago. So I didn't have a recent picture to include, and some of these students already left, students or postdocs. So to give you a taste of my research group from the name itself, it is Nano-Energy and Photonics group. Often people wonder why it is Nano-Energy and Photonics groups. And many people think that, okay, these are two different extremes, especially the energy or the materials or the photonics. Of course, all the optics, electronics, and everything comes under material science too. But these are the two directions of my research. One is the energy, where I am going to talk mostly about this field, the supercapacitors, wearable devices, perovskite solar cells, integrated energy devices, and so on. And the other direction is the optics direction, where we do a lot of optoelectronic synapses, holographic 3D displays, optical and photoacoustic C-scan, and organic optoelectronic transistors. So holographic 3D display, we have been working on it for quite some time, and some of the early papers, especially these two Nature papers, were published about this holographic 3D display. I was hired for developing some new polymers for this application, and it was successful, and we demonstrated the three-dimensional display using these materials, photorefractive polymers. And optical photoacoustic C-scan is another field, optical field, and these optoelectronic synapses and organic optoelectronic transistors, these are two new fields we are venturing in, and it's a very, very interesting field. And in the next slide, I will give you I will only take a few seconds on that one, and then this is basically more physics oriented, and if the physics or other departments ask me to give a presentation on that one later on, I will be happy to do that one. So the beauty of this one is our brain, it has so many neurons, and how it works, how it is connected, and nobody knows it. Even the tip of the iceberg is not known how it works. So it is one of the best computers ever anyone made so far, so that is the thing, how they are connected and how neurons are connected with each other. And there, as you might know, neurons are connected to each other, or the information is transferred from neurons to neurons through synapses. And the synapses, it has electrolyte or type of liquid, and through the ions, the information is transferred. That is the reason why I see a connection between the actual electrochemistry and this type of optoelectronic devices. But it's a very beautiful area, and there are a number of applications. If you ask me why it is so important, you think about neuromorphic computing, where currently you have a processor and a memory, and you store your information in your memory and transfer it to the processor and get it processed and send it back to the memory. But in the case of a neuromorphic computing, it's very similar to your brain. If your brain is much more efficient, it needs much less energy, and that is the beauty of brain, and how brain does these things is fascinating. So that's what we were trying to understand, some of these things, how it works using these synapses, and we developed some new neuromorphic synapses which can memorize as well as it is a transistor, so it can memorize at the same time too, so it can store information. And that was recently published in this prestigious journal, Science Advances, and Nature Electronics. They publish a special report about those type of devices. So that can be used for making artificial eye, as well as a number of applications in self-driving cars and so on. So that is just the optics or optoelectronic field of my research, but a lot of other things are there. This paper deals with a lot of those things, and a new paper will be coming out soon about this one from my group, so you can tune for those reports. And the outline of my talk, I think I took some time right now for introducing all those things, but this is what I'm going to talk about is the wearable device. I just introduced the wearable devices to you, then the fundamentals of supercapacitors and energy transmitting and storing cables. I will introduce perovskite solar cells and how we were successful in making an integrated energy harvesting and storing ribbons. That is a completely integrated device where energy can be harvested and stored. And if I have time, I will briefly mention about the machine learning work we do towards the fabrication of perovskite solar cells. And finally, I give a short summary and conclusion. So introduction to wearable devices. So we are all familiar with the wearable devices. We know about Apple Watch, Fitbit, or virtual reality, and so on. Now, many of the things, you can do it on your body, or it can be even implanted into your body. That is the beauty of these wearable devices. So if you look at this one, the next slide here is like you're monitoring yourself. Rather than going to a hospital and stay there for quite some time to check all these things, if you have some wearables, these wearables are going to work like a check engine. Okay, that means it can monitor your health, and if there is any problem you have at any point, then it can alert you. Okay, it is time for you to go to a hospital, go to a doctor, and check up these things. Rather than going there occasionally or doing stuff, or if you want to check yourself, rather than staying there in the hospital, you can have this type of wearable devices, and it checks automatically, and these devices send information to remote devices or to your cell phone. So those are the beauty of this wearable devices, and this is actually in tandem with the NIH, National Institute of Health, future goal of precision medicine. So right now it is a medicine for many people. If you have some symptoms, that medicine is made for maybe a certain type of people, and also all those things. But in this case, if it can monitor your body responses. So it can be precisely made for you. That is the whole idea of this precision medicine. So there are so many other devices here: prosthetic skin, EEG, ECOG, and optogenetics, and so on. And here you can see that wearable energy devices. So these are all energy hungry devices. So in order to feed these energy hungry devices, you need to have some type of solar or energy harvesting device as well as storing device, so that it can provide energy for these wearable devices. So these are some of the already existing reports. The nature, this is a skin-like ECG machine, and you can measure all your ECG, and you can just attach it to the skin. And it was, I think, this was reported by Stanford University back in 2015, and one from University of California, I think Santa Barbara or somewhere. This, you can see that ECGs can be monitored at real time. So that is the beauty of this thing. This type of devices is transforming the healthcare. But if you have a new Apple Watch, the new Apple Watch itself can measure your ECG while you are on your daily routine. So that is, again, it is transforming the healthcare of humans. So coming to the other one, the other part, machines and equipments, where these wearables are so important. For example, I would say that semi-autonomous or autonomous cars, self-driving cars, it has a number of these type of wearables. If you look at the cameras in Tesla, okay, it has a number of cameras all around it, and then it monitors everything, and then it can go by, or it can try by itself, and so on. These are all this is a concept car from Mercedes-Benz, and here this is the Tesla Roadster, which is a beautiful car. And the Elon Musk claims that, okay, it can go from 0 to 100 kilometers in 2.3 seconds or 1.9 seconds or so, or 2 seconds. Think about it, from 0 to 100 in 2 seconds time. So now you can imagine how much energy it is necessary. It is not really just energy, it needs that huge power. So now if you look at the other one, it's a recent report about Lamborghini, that is the new, or I don't know whether it is entirely new, but a Lamborghini. This runs on supercapacitors. You might have heard a lot about batteries, and Dr. K. Abram in the last seminar talked a lot about the lithium-ion batteries, which is very essential for all these type of devices. And that talk made my life easier. So today I don't need to talk a lot about those type of things, but I'm not going to talk mostly about the supercapacitors. So this car runs entirely on supercapacitors. So what is supercapacitors? You have heard about the batteries, but not that much about the supercapacitors. So that's what I'm going to talk today. So fundamentals of supercapacitors, what are they? So the batteries, you have heard a lot about it. Energy density, you heard that it can go to this 100 to 250 to 300 watt-hour per kilogram, and it has a long discharge time, low power density, and inferior number of cycles, low power delivery. Those are the few disadvantages of lithium-ion battery. If you look at that one, inferior number of cycles and slow power delivery, and also the power density is low compared to supercapacitor. So that is given here, supercapacitor performance. But what are these two terms, energy density and power density? So energy density, I would say that your lithium-ion battery has a really good energy density. That's the reason why you can run your laptop for 8 hours or 9 hours, or depending on your battery. But if you use your supercapacitor, it cannot run your a computer or laptop for that long. But when you consider a car like this Lamborghini, okay, or a Tesla Roadster, when it needs to accelerate from 0 to 60 miles, okay, this is 60 miles, so 0 to 60 miles in 2 seconds, it needs a lot of power. And actually that power can be provided by supercapacitors. That's the beauty of supercapacitors. And also these supercapacitors can undergo so many tens of thousands of cycles. And I am not saying that, okay, supercapacitors are going to replace batteries or anything like that. They are in a supportive function. It can be used in many applications, and they are very reliable. So some supercapacitors, even in my lab, we developed some supercapacitors which can go to more than 100,000 cycles. It's not a big deal when you consider about the typical or capacitors. There it can go to EDLC type capacitors. It can go to that high cycle life, but typically their power density and energy density are lower considered compared to the other one. So I will talk about that one very briefly. So they are so reliable that it is used, these type of supercapacitors are used in the emergency doors of A380 Airbus. So that is the about that supercapacitors. Now a comparison of the supercapacitor and battery. Here you can see the battery. As you have heard in the last talk, here it is the intercalation of the ions into your electrodes. So if, for example, if this is a graphite, it has a bulk there, bulk graphite there, and these lithium ions intercalate into this bulk of this electrode or graphitic electrode. And you heard about all the layers and all those things. So that's the reason I told you that Dr. Abraham made my life easier. So now compare, here is the double layer supercapacitor. Okay, it is the EDLC. It is called electrochemical double layer capacitors, where you have this back electrode and maybe an active material on that back electrode. This is just the collector electrode where you can collect the charges. And here in this case, EDLC case, there is only electrostatic attraction between, or Coulombic, very low electrostatic attraction between these things. There is no Faraday reaction in this case. That is the point. That is the point you need to note. There is no Faraday reaction in this case for the EDLC type supercapacitors. But in the case of pseudocapacitors, you can look at this name itself. It's a pseudo. It's not the double layer capacitor. And here there is a Faraday reaction. It is somewhat similar to your lithium-ion battery, but look at this one here. There is a transition metal oxide, and this how it stores its charge. This transition metal stores its charge is changing the oxidation state of manganese from 4 to +4 to +3. And while it is changing, how that is going to be changed, it is abstracting, it is taking one electron and it is changed to Mn3, and at the same time, a sodium from the electrolyte is attached to that one. So here, a charge is stored in this material right now. So it is the opposite in the other electrode, that is a pseudocapacitor. So what is the difference between these two? Why you need a pseudocapacitor? You need a pseudocapacitor is basically because to increase your capacitance. Okay, to increase your capacitance and also the energy density, you can have a pseudocapacitor. But the downside of a pseudocapacitor is your cycle life is often limited, maybe to 10,000 and a little more than that. But we have, in my lab, there are some pseudocapacitors which can go to 35,000 and more cycles. I'm talking about the cycles, number of cycles. So is there cases where supercapacitors completely replace batteries? Yes, of course, there are cases where the astronaut, this is the, what NASA uses for the space supercapacitor bus here, a number of packets here, and they don't have time to charge it very often, so they just use the supercapacitor drill, and it is from the NASA Glenn Research website. And also Kappa bus in China, this runs just on supercapacitors, where it can run for about 4 to 5 miles stop at a certain point, and it can be recharged. This bus can be recharged without overhead lines, the charging lines. You can see in this case there are no lines, overhead lines that is running through here, so it can just stop somewhere, charge it within 3 to 4 minutes, and it can run another 4 to 5 miles and stop at the next point. So the taxonomy of supercapacitors, as I already mentioned, it is the double layer supercapacitor and pseudocapacitors, and there can be a number of materials used for these things: activated carbon, carbon nanotubes, graphene, carbon aerogels, and so on. And there are hybrid capacitors, and there can be battery type capacitors. This is the battery hybrid, this is an asymmetric hybrid, and this is a composite hybrid. And if you are interested in more into this type of different materials that can be used for supercapacitors, you can read some of our review papers on this type of materials. In this is one of the highly cited papers, and this is also for the asymmetric supercapacitor. In a minute I will explain what is an asymmetric supercapacitor. And also, if you are interested in using two-dimensional materials for supercapacitors, and we published a paper in ACS Energy Letters back in 2018, and yesterday or day before yesterday, I heard the news that that paper was one of the most top 5 cited papers in this highly prestigious ACS Energy Letters, that is an ACS journal. So what is the energy density of supercapacitors? The 2 important parameters you need to learn. I will just glance, quickly go through this one. Basically, I don't have much time, but this is the basic principle. Capacitance is given by this equation: C is equal to A into epsilon R epsilon 0 over D, which the whole point of this one is capacitance is directly proportional to the area of your electrode. Okay, and D is the double layer thickness, that is the thickness between the electrodes, or the thickness of the electrolyte, the space between the electrodes. So energy density is another important term, which is given by this equation: E is equal to half CV square. And please note that 2 of these parameters, one is for the capacitance, it is A, and here this is the capacitance into voltage. And the reason why this one is important, voltage is important, is unlike batteries, many of the batteries, we use aqueous electrolyte in supercapacitors. If you ask me, if the aqueous electrolytes are used in all the currently available supercapacitors, no. It's organic electrolyte, they use it, and there are many limitations for that one. Your lifetime is limited, as well as the powering, the charging time is more, and also more than that, many people, especially for wearable application, military and those people, they prefer the aqueous electrolyte, that is water-based electrolyte. Now look at this one. The voltage is a very important factor. It is the square of the voltage. Now the energy density of the supercapacitors using aqueous electrolyte is limited because of the voltage, if in the case of a symmetric supercapacitor. And it depends on the electrode potential window. In the case of supercapacitors, the general equation can be given by this one: E is equal to, this is electrode potential. Okay, this is not the energy density, but this is the electrode potential here, is equal to E0, which is the working potential, and delta A and delta B are the surface dipoles potential of positive and negative electrodes. And this can be written as this one. And then just rearranging it, you can get this equation. I want to come to this level. That's the reason why I'm showing it, where this the omega alpha is the electrochemical potential of the positive electrode, omega beta is the electrochemical potential of the negative electrode, and we can just rearrange this equation. So we can write it as this: the electrochemical potential plus the surface potential of one of the electrodes minus the electrochemical potential of the surface potential of the other electrode. So therefore, this is actually the work function of the electrode. In work function is the term mostly, I think, mostly I have heard in physics and in electronics, but chemists do not use that work function that often. But electrochemical potential plus surface potential, that gives the work function of the electrode 1, and this is the work function of the electrode 2. So if you consider a symmetric supercapacitor, the thing is that if you look at that equation, what is a symmetric supercapacitor? This is a symmetric supercapacitor where you use the same electrode material on both sides as positive and negative electrodes. That is a symmetric design with the electrolyte in between. This is the active ion, so electrolyte you have there in water. Okay, that's what we use. In the asymmetric one, unlike symmetric one, look at this one, there is a positive. This is a different material than the negative electrode. This is the difference between symmetric and asymmetric supercapacitors. So for the symmetric one, okay, you can see that it's the same material is used. So the delta A and delta B is equal to 0. Delta A minus delta B is equal to 0, as well as omega B is equal to omega alpha, or omega beta is equal to omega alpha. That is, the electrochemical potential of both the electrodes are same in this case. So the thing is that in this case, symmetric case, you are limited by the decomposition of your aqueous electrolyte, basically water. So your voltage is limited to about 1.24, which is the decomposed 1.24 volt, which is the decomposition potential of your water. So you can see hydrogen and oxygen evolution in that case. So here, I am just showing you, this is the work function. That is from the energy from vacuum to the Fermi energy level. This is the work function, this is the electron affinity, and this is the ionization energy. But in the case of electrode potential window for the asymmetric supercapacitor, you can see that these are two different materials. So it is delta A minus delta B is no longer equal to 0, and the omega beta is no longer equal to omega alpha. So electrochemical potentials are different, as well as the surface potentials are different. Now it is no longer dependent on the decomposition potential of your electrolyte, but now it depends on the work function difference of the two electrodes. Okay, that is the key point you need to remember. Now your voltage window is dependent on the work function difference of the two electrodes. So what is the take-home message from here? The message is this one: by suitably or intelligently optimizing the material work function, you can get a higher voltage window than that 1.2 volt or so. So if you can tune the work function of your material, there are many methods to do that one, you can get a voltage window higher than 1.2. And in my lab, we were able to get, right now by doing some of the modifications, these are unpublished reports, but again, more than 2.4 to 2.6 volts. So how we measure this work function? Typically, we use the Kelvin Probe Microscopy, that will give you the ideal work function, which is going to be felt by the electrode in your machine, in your supercapacitor. So we use the Kelvin probe method to measure the work function, and there is a recent paper just accepted on this type of determining the work function of this electrodes using this KPFM method. And but it is not detailing more than that. But there will be another paper coming up soon, which is going to deal with this type of modifications and such things. So, coming to the next one, the energy transmitting and storing devices, I have already finished a lot of my time, but I'm talking about the smart fabrics, the fabric which can be used to do all sort of things, like it can be used as a communication device and a wearable device. All those things, especially for soldiers, is extremely important. So if we can make a coat using energy storage device, instead of having a lot of batteries right now, American soldiers, they carry about 28 to 40 pounds of battery on their body. So depending on what get rid of some of that battery weight if you can convert some of your fabric or the clothes into energy storage device. So one of the first directions or steps is done by my group, at least in the supercapacitor direction. That is where we try to make some fibers which can store energy. So this is the first attempt we made in that direction. So people have been working a lot on the planar supercapacitor device. Even my lab was using it, but we thought about it now if we can convert some of the copper wires into storage device too. So the same copper cable or the fiber can be used to transmit electricity. As you know that there are millions and millions of kilometers of copper cables around the world. If you can use some of that copper cable to store energy too, that would be ideal, So that's the first initiative from my group on this wearable type energy storage device. It's a very simple technique we used the copper wire, and by heating the copper wire, you can convert that copper wire into copper oxide, nano viscous. So copper oxide is an insulating material, so you may need to have another material on top of it, conducting material, to make it into an electrode. So we deposited another material like gold palladium. There is nothing special about that gold palladium. You can use copper as well. So we electrochemically deposited an active material on this nano viscous, and now this is an active electrode itself. Remember, the inside is still copper, but the inside copper is insulated from the outside because of the presence of nano viscous. So then what we did for the other electrode is we just took copper foil and it heated to a higher temperature, and then you can see that here the copper nano viscous are formed. Then we deposited that gold palladium onto it, and then here is the copper oxide, gold palladium, manganese dioxide. Then we took this one internal wire, and then we wrapped that internal copper wire with this thing, this outside copper foil, to get a supercapacitor. Here you can see some SEM image of the nano viscous. It's a beautiful structure, with the nano viscous about 200 nanometer diameter and 20 to 22 microns height. So you can see that aspect ratio is very high in these cases. So this can be done very easily, and this is the process we use. This is the internal cable and the separator and the outside covering. So that's the first report that was published in Advanced Material, and here is the electrode performance, which shows that it's a reasonably good storage device. The outside can be used for storing energy, and these are at different scan rates, and these are all typical electrode characterizations, and with the thickness, how the specific capacitance increases, the thickness of manganese dioxide, and so on. So the performance is given here. The specific capacitance is 493 farads per gram after a number of scans, as well as bending and all those things. This is the GCD showing the performance of the supercapacitor cable. So here is the cable, the performance. If you bend it to different angles, you can still see that it can retain a very high capacitance, and even after 5,000 cycles, it can retain about 99% of its capacitance. And this is a Ragoon plot which shows the energy density to power density compared to other similar devices, and this is our device which gives a really good performance. So the beauty of that device is this one. This is the first report by anyone about a cable which can transmit electricity and at the same time it can store energy. So that's what we demonstrated here by this type of measurement. Okay, so it has a number of applications, and since it was a first invention in this direction, even the Nature came up with a 2-page report about this device. So, and a number of people were also interested. And here, you know, this is just a video showing that this is one of the cables we developed. This can be extremely thin as well as thick, depending on your application. And if you can see this video, you know, initially they charge this cable from this power source, and then they just take out these cables and they demonstrate that this fan, this is a reasonably big fan, and this fan can be operated just using these cables. So here, I hope you can see this video. Tomla, can you see this one?
Yes, we can. We can see it. Yes.
Okay. So this is the performance, and now it's operating just from that cable. So that is the that's the working of this one. So you may ask me why it is so important. For if you consider just for this application, it's an IC. Integrated circuit, and right now you have this type of CAN type the supercapacitors, and these CAN type of supercapacitors can be replaced by this type of cables, you know, and you can see how much real estate, how much space you can generate by just removing those CAN type supercapacitors from that ICs. So even, you know, in this case, you don't need to have it here. You can run these cables through the sides. That's the advantage. So there were a number of reports about that one, and a number of news agencies were very much interested. So this work is another one where we use the carbon fiber, and this is a carbon fiber, and we use this graphene to vertically align onto that carbon fiber. Remember, your capacitance depends on the surface area of your electrode. So by vertically aligning this carbon fiber with this graphene, you know, it's a beautiful structure. You can see that they are well aligned, and it gives a lot of surface area. So that was this is a recent report in small in 2019, and then we demonstrated that we can make a asymmetric or a symmetric supercapacitor out of this one. And look at this one; it has a cycle life of more than 100,000, with the very little degradation of the performance. So that is the beauty of this one, this type of devices, the fiber type supercapacitors. And now, if you look at this one, this is the performance, and the same device can have both double layer capacitance as well as pseudo-capacitance. That means the Faradaic reaction and non-Faradaic reaction. And here in this case, here you can see that all the double layer capacitance which comes from that graphene. It is here, and this is the pseudo-capacitance basically because of the heteroatoms present on some of that graphene oxide. And this is you know, the carbon fiber, just a carbon fiber, and we use that carbon, you know, cloth type structure to make, you know, to run this propeller of a toy plane. Okay, so that's what you can see here. And then I'm moving to the perovskite solar cells, but since I don't have much time left, I'm not going deep into this one. But perovskite is a new material which is very interesting, and unlike silicon solar cells, you might have heard a lot about the silicon solar cells, and the efficiency is maybe 25, 26 for a highly crystalline silicon solar cell. But a new material, a new type, perovskite is, I'm not saying perovskite is a new material, but this perovskite solar cell came out recently back in 2008, that time, and started with an efficiency of less than 5%. And now the efficiency, if you look at this one, this is the NREL chart, that is DOE, the Department of Energy chart, where the efficiency is 25.2. That is the current efficiency of perovskite solar cells. It is nothing but a methyl ammonium lead iodide. This is the formula for that AbX3 type crystals. So the advantage is this material has more excitone binding energy, unlike the organic materials. A high absorption coefficient, it can absorb a lot of light, and there is a high charge mobility in this material. These are the very good advantages, and the important point you need to remember is this one is a low temperature processing, and the solution, it can be processed from the solution, and it is earth abundant, and it can be made into a semi-transparent materials. And these are some of the details about it, why perovskite is important. Its band gap is 1.1 to 2 electron volts. It can be tuned all the way, and the materials are very cheap compared to silicon. And these are some of the device structures, but there are limitations for perovskite too. You need to remember the perovskite, this contains lead. If you look at this one, it has lead, which is a toxic material, and that is always a disadvantage. And people are trying to replace this lead with some tin or other elements. But even in this case, in this perovskite, the amount of lead is very, very small. So that can be, if these perovskite solar cells can be returned to the shop, or they can recycle it, then that would be good for many applications. Also, there is a moisture sensitivity for this material. The performance degrade after some time, but there are some approaches, encapsulation and other approaches to get rid of such problems. So there are two types of perovskite solar cells, PIN and junction and NIP junction, and this is the geometry which we typically use: cathode P-type material, perovskite absorber, and so on. So I'm going through this one very quickly so that I can talk more about the more interesting stuff about the energy harvesting and storing devices. So we developed a new method to make this type of perovskite solar cells. It is called a PCBM assisted growth, and we published this work back in Journal of Material Chemistry back in 2016, and we were able to show we were able to make a semi-transparent solar cell. Here you can see this is a semi-transparent solar cell. You can see through that one, and this device can give about 8% or 9% efficiency, and its average transmission is 18% compared to your sunglass, which is about 17%. So this means that this type of solar cells can be prepared, and if we can use these solar cells to screen the sunlight, if you have the glass window there, and whatever light passing through that one is, if you want to screen the light, that light is wasted. But if you have this type of semi-transparent perovskite solar cell or solar cells, it can harvest that energy and convert that energy for useful applications. That's the whole idea behind this one. So now, previously I talked about the cables, fibers which can store energy and transmit electricity. But think about it, if people are outside for the many people, soldiers, first responders, police, and so many people, they work outside a long time, especially firefighters and soldiers, So it is not practical to go inside and charge your energy device, a storage device. So that's the reason why we thought about this one. Why don't we integrate these two devices together? That means if we can integrate the solar cell and supercapacitor, and that would be really nice. Currently they are two separate devices. They are not completely integrated. There is a solar cell or a supercapacitor or a lithium-ion battery, and they are connected with each other. And this affects the mobility of this device. You have a solar cell sitting somewhere and a grid somewhere else, and you are transmitting all your energy from the solar farm to the grid. That is the problem. So if you have a completely integrated device like this one, this is going to be highly beneficial. So we looked at the energy levels of the material, different materials that can be used in this these devices, and very carefully engineered these energy levels so that the electrons generated by illuminating these solar cells, it can be directly transferred to this electrode. And this electrode is made up with so many nanostructures on this side, and these electrodes can be directly stored in this material on this side. But outside, this electrode should be connected to this one, the other electrode. So this we came up with this idea, and we demonstrated that this can be done, and by making the solar cells. These are the nanostructures we developed for the supercapacitor, the nanotubular structure we developed for this application. And then we demonstrated that, okay, this supercapacitor can be made, and you look at this one, you can see that supercapacitor, it can go to a number of cycles, more than 10,000 cycles, without much degradation of the property. So then we integrated these two devices. Okay, we first make a supercapacitor, and then make the other device, the solar cell, on the other side of that same copper filament. This is a copper ribbon, actually. You can see that this is the copper. This is an American penny, which is very small, and you can see that this is the ribbon with the solar cell on one side and supercapacitor on the other side. This is just to show that even after integration, you can get the same performance from your device. So here you can see the performance of the device. Okay, here you are using a light source or a solar simulator, and you charge your solar cell. Now at this point, you just turn off your light, and now you discharge it at different currents. Okay, so 1 ampere, 2 ampere, that's what you can see here. So this is the Ragoon plot, which shows the energy density and power density and all those things. And for a wearable application, you need to have it highly flexible and bendable. And this is to demonstrate that, okay, with the different bend angles, it still gives more or less very similar performance. So this is the performance of two ribbons in series to get higher voltage and so on. And then what we have done is we bought a loom, and at that time I had a student or a postdoc who knew how to weave these things, and he helped us to weave these fibers, these ribbons, along with the fibers, cotton filaments, to make it into a form of a small fabric. You can see that this fabric can be attached. This is very crude form, and okay, so this is just to show that it can be put it onto your coat, and it can be useful. So in the case, this is a video just showing that initially this is going to be illuminated for a few tens of seconds, and then you can see that the energy stored within this fabric can be used to light this LED lamp. Here is an LED lamp. So first I am going to run this video. So hopefully you can see that. Okay, now we are illuminating the this fabric with light. Okay, and then after this time they are going to turn off this light, and now they are connecting it to that LED. So you can see that LED can be lighted just with the energy stored in that fabric. So that is the beauty of this type of, that is the basic principle behind it too. So that is the demonstration we have done. That is one of the first wearable energy smart ribbons for synchronous energy harvesting and storage devices. It was also very interesting for many people, and even the National Geography, they published a report about it, about this type of wearable clothes and such things. So What is the application? A lot of application in this case for the military application, you know, and also for the cars and all those things. If you can make solar use, for example, a self-charging device here, a platform like this one, a matrix, and if you can put it on top of your car for an electric car, and if you park it outside in the sun during the daytime, what you can do is you can harvest energy from the sunlight. You can store it in the same that matrix, and by the end of the day, by evening, you may be able to drive another 5 to 10 miles or so. So that is the whole idea of this type of devices. So I think I already passed 60 minutes, so I don't think I have enough time to do it, but this is just to show you that perovskite solar cells can be optimized using this machine learning, and this is one of the work we have recently done. We have used the machine learning and optimized the structure of the perovskite material. And here you can see that this is the PSC band gap prediction. Then you can have different band gaps. It can vary. Okay, predicted band gap and the true band gap here. And then we experimentally showed that when you prepare some of these type of materials that can be highly used for this type of perovskite solar cells. So here you can see that PSC device physics rationalization, and from this machine learning you can get this Shockley-Queisser limit and so on without giving any information about the band gap of the materials. Just from this machine learning, we are teaching the machine to learn it, and then it can predict the band gap, best band gap required for this type of applications using this particular material. So I hope I convinced you that this is a promising field, especially for wearable devices, energy harvesting and energy transmitting, energy storing devices. And there are a number of applications which are dependent on it, present and the future applications, especially for highly integrated devices. I think these are some of our recent publications, which were the cover pages of journals. And you can see these are some of our recent publications. And thank you very much for your attendance. And I really appreciate being here. And you all turned off your microphone. And I enjoyed talking to you. Thank you.